Nobody is talking about what happened when the most controversial AI system on the planet turned its analytical gaze toward the one place on Earth, or rather above it, that humanity has never truly seen. Not one mainstream outlet, not one primetime broadcast, not a single government press conference. And yet, what emerged from that intersection of machine intelligence and lunar mystery may quietly be one of the most consequential revelations of our generation. The far side of the moon has kept its secrets for 4.5 billion years. It has never once faced the Earth. It has never once been bathed in our radio waves, our surveillance, or our curiosity. It is the original blind spot. And now, an AI that itself operates in the shadows of controversy, trained on more raw data than any human team could process in 10 lifetimes, has begun pulling back the curtain. What it found doesn't just change what we know about the moon. It changes what we know about ourselves, our planet, and the invisible war being waged right now for control of the most strategically important piece of real estate in the solar system. There's a place that has never been seen from Earth. Not once. Not in the entire history of human civilization. Every map ever drawn, every telescope ever pointed skyward, every astronaut who ever floated in the dark void of space and looked back at the moon, none of them have ever seen this place directly. It sits permanently hidden, forever facing away from us, locked in a gravitational arrangement so precise it seems almost deliberate. We call it the far side of the moon. And for most of human history, we simply accepted that it was unknowable. But here is what nobody is telling you. In the last 18 months, the combination of China's Chang'e 6 mission, returning the first physical samples ever extracted from the lunar far side, advanced AI systems processing petabytes of orbital imaging data, and the emergence of analytical tools like Grok that can synthesize scientific data sets at a scale no human research team could ever match, all of this has produced a convergence, a cascade of revelations that, taken separately, each seem remarkable. Taken together, they paint a picture that should stop every geopolitical strategist, every defense analyst, and every ordinary person who cares about the future of this planet dead in their tracks. Because this is not just a science story. Read that again. This is not just a science story. China's Chang'e 6 mission changed everything when it returned 1,935.3 grams of material from the lunar far side's South Pole Aitken Basin, the moon's largest, deepest, and oldest known impact structure, measuring at 2,500 kilometers in diameter. Think about what that means for a moment. The most ancient scar on the surface of our moon, a crater so enormous it stretches across a distance roughly equal to the width of the continental United States. And for the first time in the history of science, we had physical pieces of it in our hands. But getting the rocks was only the beginning. What happens next is where the story turns from remarkable to genuinely unsettling. When you feed 1,935 grams of ancient lunar material into the most sophisticated analytical instruments on Earth, when you combine that chemical fingerprint with spectral imaging data gathered from Japan's Kaguya lunar orbiter, when you then train artificial intelligence systems to cross-reference every data point, every isotopic signature, every mineral gradient against decades of orbital mapping, something extraordinary emerges. Researchers at Shanghai's Institute of Technical Physics trained an AI model on chemical measurements and spectral data from the rocks, then fed it high-resolution images from Japan's Kaguya lunar orbiter. The result was the first precise global map of the moon's major oxides: iron, titanium, aluminum, magnesium, calcium, and silicon, revealing how these elements are distributed across the entire far side. The first complete chemical portrait of a hemisphere that has been invisible to humanity since the beginning of time. Let that sit for a moment. And what did that portrait reveal? The chemistry tells a story of three distinct regions. There are the dark volcanic plains called Maria, the bright ancient highlands that make up most of the far side's crust, and the vast South Pole Aitken Basin itself. But it is what those regions revealed about the moon's internal history that began to shake the foundations of established science. The South Pole Aitken Basin, formed by a colossal impact approximately 4.25 billion years ago, releasing energy greater than that of 1 trillion atomic bombs, yielded 4 landmark discoveries, 1 trillion atomic bombs. And scientists had long suspected this impact happened. But suspected and proven are very different things. Because now, with AI-processed data illuminating the chemistry of that impact zone in unprecedented detail, the sheer geological violence that shaped the far side of our moon was confirmed in a way that rewrote textbooks overnight. But here's where it gets worse, or rather, stranger, and more interesting. The samples contained volcanic rocks called basalts that date to prolonged volcanic outbursts on the lunar far side in 2 distinct phases, one around 4.2 billion years ago and another 2.8 billion years ago. 2 separate volcanic episodes separated by over 1 billion years. This is significant because the dominant scientific assumption about the moon had been one of relative geological simplicity. The moon was supposed to be mostly dead, geologically inert, a cold, stable body whose violent past was ancient history. What the AI-driven analysis of these samples revealed instead was a moon that was far more geologically complex, far more internally dynamic, and far more mysterious than any model had predicted. Think about what that means for the models we have been relying on to understand planetary formation. If we were this wrong about the moon, a body we have been studying up close for over 60 years, a body our astronauts walked on, a body within visual range every single night, then what assumptions are we making about other planets, other moons, other bodies in the solar system that are just as fundamentally incorrect? But the volcanic history is only the first revelation. Because waiting beneath the surface of the lunar far side is something that should not exist, something that, by every scientific rule we have established about planetary geology, cannot exist. And yet, there it sits, emitting heat, defying explanation. Scientists have identified a region roughly 30 miles or 50 kilometers wide on the far side that is about 18 degrees Fahrenheit, warmer than the surrounding area. 18 degrees. On the moon, in a location where temperatures are supposed to be uniform and predictable, a zone the size of a major city is anomalously, inexplicably, stubbornly hot. Now, you might think that a temperature difference of 18 degrees is minor. You might think it barely warrants some attention. And if this were Earth, you might be right. But for scientists studying a body like the moon, a difference of 18 degrees in a localized zone is like discovering a fire burning in the middle of a frozen ocean. It is a screaming signal that something beneath the surface is fundamentally different from everything around it. And when researchers drilled into the data to understand why, the answer they found challenged something that had been considered settled science for decades. The likely culprit is a massive block of granite buried beneath the surface, a rock type common on Earth, but almost unheard of on other planets or moons. Granite on the moon. Let that fully register. All the textbook ways of making granite involve these processes that only happen on Earth, said lead scientist Matt Siegler, a planetary scientist at the Planetary Science Institute. How do you recreate this process? Because on Earth, granite forms through a very specific sequence of geological events. It requires water. It requires active plate tectonics. It requires pressure, heat, chemistry, and time working together in a combination that we had firmly believed was unique to our own planet. The moon has none of those things. The moon never had plate tectonics. The moon is bone dry. And yet, there beneath the far side is a batholith, a massive underground granite formation, roughly 50 kilometers across and 20 kilometers deep, heating the ground from below. This is not chaos. This is a mystery, a deep structural mystery about how planets form, about what conditions allow certain types of rocks to exist, and about whether the rules we thought governed planetary geology are actually as universal as we believed. And this is where the AI angle becomes not just interesting, but genuinely important. Because these anomalies did not emerge from a single mission. They did not emerge from a single data set or a single team of researchers working over a weekend. To uncover the thermal anomaly, researchers analyzed measurements taken by a multinational array of lunar missions, including China's Chang'e 1 and Chang'e 2 lunar probes, NASA's Lunar Prospector, NASA's Lunar Reconnaissance Orbiter, India's Chandrayaan 1, and data from the Apollo missions. Multiple nations, multiple decades, multiple instruments, multiple languages, multiple scientific traditions, all generating data that no human team could have synthesized into a coherent picture alone. The scale of integration required to pull these threads together, to identify the patterns buried across petabytes of orbital imaging and spectrographic data, is precisely the kind of task that artificial intelligence was built to perform. When Grok and similar AI systems are pointed at problems of this magnitude, not as chatbots generating casual responses, but as analytical engines processing scientific datasets, they reveal things that human researchers, working within the natural limitations of human cognition and human collaboration, simply could not have found at this pace. The granite anomaly at Compton-Belkovich on the lunar far side had been suspected. The thermal signature had been noticed in isolated datasets, but it took the convergence of AI-powered cross-referencing to confirm the full scale of what sits beneath the surface. The research team believes this heat signature may be the remnant of a volcano that went dormant some 3.5 billion years ago, with residual magma trapped deep underground, still emitting faint thermal radiation detectable today. A 3.5 billion-year-old geological engine. Still running, still radiating, still hiding on the side of the moon we have never seen. But now, step back. Because if this were only a science story, it would be fascinating and it would end here. The problem is that it does not end here. Not even close. Because the moment you understand what the far side of the moon actually contains, what resources sit in those ancient craters, what strategic value exists in that permanently shadowed real estate, what the first nation to establish a permanent presence there will actually control, the science story dissolves into something far more urgent, far more dangerous. Unlike the first Space Race 2.0 is about defining the norms, rules, laws, and infrastructure that will guide the future of space exploration. The U.S. lunar program is delayed, while China has pledged to put astronauts on the moon by 2030, and it has a habit of sticking to timelines. Read that again. The United States, the nation that put 12 men on the moon between 1969 and 1972, is behind schedule, and China, which had never landed a crewed mission anywhere, is on track to beat them to the return. This is not a minor diplomatic embarrassment. This is a strategic realignment of the highest order. Because what makes the far side of the moon uniquely valuable is not just its mysterious geology, though that is remarkable enough. What makes it irreplaceable is its silence. The far side of the moon is the only place in the entire cislunar environment that is permanently shielded from Earth's electromagnetic noise. Every radio frequency we generate, every satellite transmission, every telecommunications signal bouncing through our atmosphere and into space, none of it reaches the far side of the moon. It is a natural radio quiet zone of incomparable quality. For deep space communications arrays, for radio telescopes capable of hearing signals from the farthest reaches of the universe, for military communication systems that operate below the threshold of Earth-based detection, the far side of the moon is the single most valuable piece of territory in the solar system. And China landed there first. Chang'e 4 touched down on the far side in January 2019. No other nation has done it since. No other nation has followed. And the data collected there, the scientific understanding now being augmented by AI analysis, is exclusive to one geopolitical actor. Think about what that means in terms of the intelligence advantage being built in real time. Chinese scientists used AI to determine the chemical makeup of the moon's far side, and it enabled the creation of the first high-precision global distribution map of major oxides on the moon. The first, not one of the first, not among the leaders, the first. Every nation that wants to understand the chemical geography of the lunar far side, to know where the mineral concentrations are, where the helium-3 deposits might be clustered, where the water ice sits in the permanently shadowed craters, where the most structurally stable terrain for a base might exist, is now working from a map that China drew, using China's samples, using China's AI models. This is not speculation about a future scenario. This is the operational reality of July 2026. And what does that map reveal about resources? Research led by Beihang University, combining high-resolution X-ray microcomputed tomography with advanced deep learning algorithms to virtually reconstruct over 349,000 individual lunar soil particles, found that the far-side regolith is significantly more irregular in shape than near-side counterparts, leading to higher shear strength. Higher shear strength means better structural stability. It means the far-side soil is actually more suitable for constructing permanent infrastructure than the near side. It means that whoever builds on the far side first is not just claiming symbolic territory. They are potentially claiming the most engineerably advantageous real estate on the entire lunar surface. And the moon is not just about science anymore. The moon is about helium-3. It is about the water ice sitting in craters that have not seen sunlight in billions of years. Water that can be split into hydrogen and oxygen, becoming rocket fuel, becoming the gas station for every mission going deeper into the solar system. Whoever controls lunar water controls the economics of all future space exploration. The moon is not a destination. It is a choke point. And the far side, with its silence, its stability, its ancient geological richness, is the choke point within the choke point. The Artemis 2 mission took 3 U.S. astronauts and 1 Canadian farther from Earth than humans have ever traveled as they flew by the far side of the moon in April 2026. They flew by it, past it. They looked at it through windows. But they did not land on it. They did not plant a flag on it. They did not drill into its ancient regolith and bring back samples that an AI system could use to map its chemical architecture. They flew past it, and then they came home. Meanwhile, China is building, methodically, patiently, systematically. The International Lunar Research Station is not a proposal. It is a project with a timeline, with hardware and development, with a partner network that includes Russia and is expanding across the global south. And the site selection for that station draws directly from the AI processed analysis of Chang'e mission data, from precisely the kind of resource and terrain mapping that no other nation has yet replicated. But here is what most analysts are not discussing. The race for the moon is inseparable from the race in artificial intelligence, because the nation that can process lunar data faster, that can identify resources and anomalies and structural opportunities at machine speed, that can plan missions based on AI-driven simulation rather than years of human deliberation. That nation has a compounding advantage that grows with every new data set. Every sample, Chang'e returns. Every orbital pass, every seismic measurement, every thermal reading feeds into models that become more accurate, more predictive, more strategically useful. The AI advantage in space is not a one-time edge, it is a flywheel. And once it builds momentum, the gap between those inside the flywheel and those outside it becomes very difficult to close. AI has already detected several significant anomalies on the moon, including volcanic pits and skylights, collapsed sections of lava tubes that could serve as future lunar habitats, offering protection from radiation and temperature extremes. Lava tubes, vast underground tunnels carved by ancient magma flows, their ceilings intact, their interiors shielded from cosmic radiation and micrometeorite bombardment, and the brutal temperature swings that make the lunar surface so hostile to long-term human habitation. A human being standing on the lunar surface is exposed to radiation levels roughly 200 times higher than on Earth, inside a lava tube that drops dramatically. The lava tube is not just a geological curiosity. It is a ready-made habitat, a natural shelter that could house a permanent human presence with a fraction of the engineering complexity required by surface-based structures. An AI is mapping them, identifying their locations, estimating their structural integrity, flagging the ones most suitable for human occupation. The database of potential future habitat sites on the moon is being built right now, invisibly, by machine intelligence, processing decades of orbital imaging at speeds no human team could match. Now consider the timeline. Private missions are expanding lunar exploration, with Firefly Aerospace's Blue Ghost set to attempt a landing on the far side of the moon in the second quarter of 2026 on a SpaceX Falcon 9 rocket, carrying a small rover from the UAE. Private companies landing rovers on the far side, not governments. Private companies with their own data rights, their own resource agreements, their own relationships with AI firms that can process whatever their rovers discover. The commercialization of lunar exploration is accelerating in parallel with the geopolitical competition. And the combination of those two forces is creating a situation where international space law, which was written in 1967 when the moon was an abstraction rather than an operational theater, is completely unprepared to manage what is coming. In civil space, norms and industry standards are filling some gaps, but they cannot match the speed of today's activity. Satellites carry enormous strategic value for civilian infrastructure through GPS, weather tracking, communications, and timing for financial networks and other critical systems. The legal framework governing who can claim what, who owns the resources extracted, who has the right to establish exclusion zones around valuable sites, none of this has been settled. None of it. The Artemis Accords, signed by the United States and its partners, establish some principles. China and Russia have not signed them. They are developing their own framework. The moon is heading toward a situation where two competing legal architectures, backed by two competing sets of military and economic power, apply to the same territory simultaneously. That is not a formula for stability, and understand what the AI dimension adds to this instability. When AI systems can analyze a patch of lunar terrain and identify its resource potential in hours, when they can simulate the construction of a competing nation's proposed base and calculate exactly which ridgelines and crater rims offer the best strategic coverage of that base's approaches, when they can model the economic value of water ice deposits with the precision of a financial instrument, the competition for the moon is no longer driven by slow-moving bureaucratic timelines. It is driven by machine speed. And machine speed is a fundamentally different kind of urgency than anything space policy has ever had to manage before. The moon's interior is not uniform, with fewer heat-producing elements on the far side, explaining its colder interior, while theories range from ancient cosmic collisions to Earth's gravitational pull. The moon is a record, a geological archive. It does not have plate tectonics to recycle its crust, no weather to erode its surface features, no biological processes to contaminate its samples. Every impact, every volcanic episode, every thermal fluctuation is preserved in its rocks with extraordinary fidelity. When AI processes those rocks, it is not just reading the moon's history, it is reading the history of the early solar system, of the conditions that allowed Earth to form and life to emerge, of the bombardment events that may have delivered water and organic molecules to the young Earth in the first place. Samples from the Chang'e 6 mission show that the lunar magnetic field rebounded in field strength after its previous sharp decline, and an estimate of water abundance in the lunar mantle indicates that the far-side mantle is potentially drier than its near-side counterpart. A magnetic field that collapsed and then partially recovered. A mantle drier than expected. Each of these data points is a piece of a puzzle that spans billions of years, and AI is assembling that puzzle at a pace that is genuinely breathtaking. Models that used to take years of analysis to refine are being updated in months. Theories that used to require new missions to test are being evaluated against existing datasets being reprocessed with new algorithms. The moon is being re-explored without anyone leaving the ground. But here is the most important thing to understand about where all of this leads. The discoveries being made right now, the granite anomaly, the lava tube networks, the chemical maps, the thermal signatures, the magnetic history, are not academic. They are operational intelligence. They are the reconnaissance data for the most consequential territorial competition humanity has ever attempted to conduct in an environment it has barely begun to understand. If AI like Grok begins routinely generating new technologies and scientific principles, the pace of innovation could increase not linearly, but super exponentially. Within a few years, we might witness breakthroughs in medicine, sustainable energy, and space exploration that transform civilization in ways difficult to fully imagine today. That is not hyperbole. That is the assessment of researchers and engineers who are watching it happen in real time. The compounding effect of AI-driven discovery means that the gap between today's understanding of the moon and what we will know in 5 years is potentially larger than the gap between 1969 and today. And in a competition where knowledge is power, where the ability to identify resources, select landing sites, plan infrastructure, and model strategic scenarios at machine speed determines who establishes a permanent, sovereign adjacent presence on the moon first. The AI advantage is not a supporting factor. It is the central factor. The far side of the moon has been hiding its secrets for longer than life has existed on Earth. In the past 18 months, a combination of physical samples, orbital data, and machine intelligence has unlocked more of those secrets than the previous 6 decades of exploration combined. What has been revealed is a geological record of extraordinary complexity, an anomaly that challenges fundamental assumptions about planetary science, a chemical map of resources that nations are already quietly mobilizing to claim, and a strategic landscape that current international law is structurally incapable of managing. Here's the question nobody's asking out loud, but everyone who pays attention to these things is asking privately. When the first permanent human habitat is established on the far side of the moon, inside a lava tube, shielded from radiation, connected to Earth only by relay satellites because direct radio communication is impossible from that hemisphere, which flag will be above it? Which legal framework will govern it? Which AI system will be managing its life support, processing its geological surveys, guiding its excavations, and analyzing every gram of material it extracts? And here's the deeper question, the one that the data from these missions quietly raises without ever quite answering. If the moon's interior is this different from what we assumed, if granite can form without water or plate tectonics, if a heat source can sit unchanged for 3.5 billion years beneath a surface we thought we understood, what else are we wrong about? What other assumptions, so fundamental we stopped questioning them, are waiting in the darkness of the far side to be overturned? The moon has been looking away from us for 4.5 billion years. It has been watching something we cannot see from here, and for the first time, the machines we have built are beginning to figure out what that might be. The answer is not yet complete. The map is not yet finished. The geopolitical architecture for what comes next has not yet been built. The legal battles have not yet been fought. The permanent bases have not yet been planted. The resources have not yet been extracted. The strategic implications have not yet been fully absorbed by the governments and militaries and intelligence agencies that need to act on them. But the clock is running at machine speed. And the side of the moon that never faces Earth is about to become the most consequential piece of territory in human history. Whether we are ready for that or not is a question nobody has yet had the courage to answer honestly. And perhaps, given what is already set in motion, the more relevant question is not whether we are ready. The more relevant question is whether we even had a choice.